Understanding the supercell. We need to have a better understanding of where the RFD resides, which is within a supercell thunderstorm, before we can even begin to discuss it. In the world of thunderstorms, the most organized, complicated, and dangerous type of thunderstorm is called a supercell. The updraft of a supercell, which is the column of rising air, rotates in contrast to the updrafts of conventional storms, which rise and fall in a single location. It is because of this rotation, which is referred to as a mesocyclone, that supercells are able to produce enormous hail, strong winds, and of course, tornadoes. The updraft is fueled by warm, moist air that is rushing in from the front and southeast sides of the storm. Aloft, the air is dry and cold, and it sinks down the backside. Zones of instability are produced as a result of the continuous mixing of these atmospheric masses. Something extraordinary takes place on the rear flank, which is the side of this revolving updraft that is located behind the front one. It is at this point that the rear flank downdraft starts to make its appearance. What exactly is an RFD? The RFD is a descending current of air that forms on the western or southwestern side of a supercell thunderstorm. Imagine a massive invisible waterfall of air, spiraling downward and then fanning out across the ground. It's born when the storm's internal dynamics, warm inflow, rain-cooled outflow, and dry air intrusion, all collide in just the right way. As precipitation falls through the updraft, raindrops and hailstones drag air downward. When that air cools by evaporating rain and mixing with dry air, it becomes heavier and starts to sink rapidly. That's the start of the RFD. But here's what makes it fascinating. While most downdrafts are cold, the RFD can have pockets of warmth, even slightly buoyant air that helps keep the tornado alive. It's not just falling, it's wrapping, twisting, and rotating around the storm's base, feeding angular momentum back into the mesocyclone. This is the zone of chaos, where air crashes downward and swirls back up again, and where nature's most violent winds can be born. How the RFD forms. In the past, meteorologists believed that the RFD was a single downward gust. However, recent study has shown that it is a far more complicated structure that is continually changing and is impacted by temperature gradients, humidity, and even sunshine, among other factors. When the sun shines on one side of the storm, it might cause the local pressure differential to become more pronounced. In the meantime, the whirling updraft of the storm is responsible for drawing in dry air from above. Because of the quick cooling caused by the rapid evaporation of precipitation and the mixing of dry air with moisture, the air is driven downward like an unseen piston. What is the end result? There is a downward spiraling downdraft that encircles the mesocyclone like a coil that is getting tighter. When the air that is falling meets the surface at ground level, it causes a powerful gust front to extend outward in all directions along the surface. When this occurs, you may notice that dust is kicking up, trees are bending, and rotation is intensifying near the wall cloud. This is a warning sign that a tornado may be approaching in a matter of moments. How the RFD fuels a tornado. Now we reach the heart of the storm, the RFD's role in creating and sustaining a tornado. Picture this. Warm, moist air is being pulled upward into the mesocyclone, spinning like a slow-moving top. Meanwhile, the RFD, colder, denser air, is wrapping around that updraft, squeezing it. This tightening motion increases angular momentum, the same physics that make a figure skater spin faster when they pull in their arms. At the boundary where the RFD's cool air meets the warm inflow, rotation can intensify rapidly. The low pressure inside the mesocyclone drops even further, and condensation forms a visible funnel cloud. If the RFD air isn't too cold, it helps sustain the rising motion by wrapping gently around the updraft, focusing the tornado's base. But if the RFD becomes too cold and dense, it can undercut the updraft, cutting off the tornado's inflow and causing it to weaken or dissipate. That's why meteorologists sometimes call the RFD both the creator and the executioner of tornadoes. It's a delicate balance, one that determines whether a storm produces a brief EF0 or a long-track EF4 monster. Scientific research and discoveries. For decades, scientists have been chasing storms to understand the RFD better. Projects like Vortex 1 in the 1990s and Vortex 2 in the 2000s sent teams armed with Doppler radars, weather balloons, and instrumented vehicles right into supercells. What they found reshaped our understanding of tornadogenesis. They discovered that the RFD often forms as a horseshoe-shaped region of descending air wrapping around the mesocyclone. Within that horseshoe, the temperature can vary dramatically, sometimes warm, sometimes cold, and that difference affects whether a tornado forms at all. Modern radars have even captured the RFD feeding air directly into the developing tornado's circulation, injecting momentum like fuel into a turbine. In one famous case, the El Reno, Oklahoma tornado of 2013, mobile Doppler radars recorded RFD winds exceeding 120 miles per hour, wrapping around the storm's base. Those winds helped the tornado rapidly expand to 2.6 miles wide, the largest ever recorded. But minutes later, the RFD cooled and dried out, cutting off the tornado's inflow and causing it to collapse. This pattern has repeated in many documented storms. The RFD gives life, then takes it away. The human side, warnings and recognition. When meteorologists issue tornado warnings, they're not just tracking funnels, they're watching the structure of the RFD. On radar, the RFD often shows up as the hook echo, a hook-shaped appendage on the southwest side of a storm. Visually, storm chasers look for the clear slot, a bright gap between rain curtains, signaling that the RFD is wrapping around the wall cloud. When that slot appears and rotation tightens, a tornado is often seconds away. Understanding these patterns saves lives. Every bit of knowledge about how the RFD behaves gives forecasters precious extra minutes of warning. The mystery that remains. Despite decades of research, the RFD still holds mysteries. Why do two storms with almost identical structures behave differently, one producing a long-track tornado, the other none at all? Scientists suspect the answer lies in microscopic changes, tiny differences in humidity, wind shear, or surface heating that alter the RFD's temperature and buoyancy. New technology, including drones and phased array radars, is helping meteorologists measure the RFD more precisely than ever before. Each discovery brings us one step closer to predicting exactly when and how tornadoes will form, and perhaps even when they'll end. The RFD is not just a downdraft, it's the pulse of the storm, a living system that connects the sky and the earth in one violent breath. So, the next time you see a tornado on the news or in the distance, remember, it's not just a random funnel. It's the product of a perfect, terrifying balance between rising and sinking air, energy and destruction, creation and collapse. And right behind that spinning column of wind lies the true architect of the storm, the rear flank downdraft, the silent sculptor of tornadoes. If you found this breakdown fascinating, give this video a like, subscribe for more science explained simply, and hit the notification bell so you don't miss future deep dives into the wonders and dangers of our atmosphere. Until next time, stay curious, stay informed, and stay safe.